which is Professor Dana Kulić, who is a professor at the Department of Electrical and Computer Systems Engineering, Monash University. And she's also head of the Monash Robotics Precinct. And her research focuses on robot learning, humanoid robots, human-robot interaction, and mechatronics. And she also aims at developing autonomous systems that can operate in concert with humans using natural and intuitive interaction strategies while learning from user feedback to improve and individualize operation over long-term use. So over to you, Dana.
Thanks very much, Layman. Let me just share my screen. Are you able to see my screen?
Yep.
Excellent. So hello, everyone, and thank you very much to Chuang, Xiang, Laymin, Zhao, Xiaofeng, Aigo, and Adriana for organizing this workshop and for inviting me to participate. So as Laymin mentioned, I'm interested in machine learning in the context of human-robot interaction. And since the topic of this workshop is around healthcare, I want to talk today particularly around how we can use learning in healthcare applications. And I'll focus specifically on Parkinson's disease because that has been the focus of much of our recent research in this domain. So before starting, I'd like to highlight the importance of context when we're developing learning approaches that are targeted to human-robot interaction or human-machine interaction applications. So there's a lot of different context variables that will influence, what algorithm is an appropriate choice. So one part of the context is what are the roles? So do we have a human teacher and a robot learner? So this might be a common configuration when we have a human expert that's trying to teach the robot how to do something. So for example, if we have a new domestic robot that has been introduced in somebody's home, the homeowner might be telling the robot, this is how I'd like you to do the things that you're going to do. Another role assignment might be that we have a robot teacher and a human learner. So this might be common in a rehabilitation context where the robot is trying to guide the user towards some target motion profile or performance level. And we could also have human robot peers where the robot and the person are working together to accomplish a shared task. So an example that you can see in that image is a surgery robot where the robot is assisting a surgeon during something like laparoscopic surgery. Another aspect of the context is what is actually the learning task? So what does the robot need to learn? So does the robot or the agent need to estimate some latent human state from the sensor observations? So for example, maybe we want to estimate what is the state of the disease from some camera or wearable data that we're collecting from the user. Does the robot need to learn what the objective of the task is? Or is the objective already known and shared? And what the robot needs to do is to come up with an optimal or good enough policy for achieving that objective. And then most importantly, part of the context is what can the robot or the agent assume that they know about the human partner? So could there be different levels of expertise? Do we have a good model of how the human partner is likely to behave during the interaction? Can we assume that most of the people interacting with the system will behave in the same way so that we have some shared commonality so that we can use data from past users to help us behave better or respond better with new users? Or is it the case that individual characteristics dominate and maybe changing with time, so that we really have to be very careful about using any information from other users and applying it to this user? So in this talk, I want to share two different examples that highlight different types of learning tasks and assumptions that we can make about the human participants. So in the first example, I will look at a case where the learning task is a mapping from sensor data to user state. So in this case, we're dealing with supervised learning, and where we try to solve the problem by assuming that there are shared commonalities between different users and that we have some model information that we may be able to leverage to help us solve this task. So the particular example is Parkinson's disease monitoring. So this project was carried out while I was at the University of Waterloo, and this was a collaboration with the Technical University of Munich and the Schön Clinic. So in this project, we were investigating the utility of using wearable sensing for continuous Parkinson's disease motor state monitoring. So Parkinson's disease is a progressive neurological disorder that results in motor disturbances. So it generates these characteristic symptoms that you can see in this video, and this is known as bradykinesia. So you have stiff, restricted movement that may be accompanied by this characteristic PD tremor. So these symptoms, these motor symptoms, can be treated with medication. So for example, medication like levodopa, but over-medication can also result in motor symptoms. It can result in uncontrolled movement that is known as dyskinesia. And so I'm showing an example. These videos were collected with patients at the Schön Clinic. So in current clinical practice, patients must go to the clinic and be observed by a clinician to assess the level of symptoms. And based on this assessment, the clinician will adjust their medication. So the objective of the clinician is to eliminate the bradykinesia symptom, but not give so much medication that patients get these dyskinesia symptoms. So now, because these assessments have to happen in the clinic, they don't happen very frequently, and this is not ideal because the symptoms may vary over the course of the day and between clinic appointments. And so it would be much better if the symptoms could be monitored more frequently, and hopefully that could lead to better medication dosing to better control the symptoms. So in this project, we wanted to develop approaches for continuously estimating the PD symptoms. And what we were interested in is having a single wearable sensor at the wrist that patients could wear every day, all day in their home environment as they go about their daily lives. So what we wanted here is not to, so in the clinical setting, the patients will be asked to perform a specific task. So either they're just seated or they're asked to maybe do sit to stand. But we wanted to allow the detection of symptoms no matter what the activity is that they were engaged with. So we wanted to have them to be able to have continuous symptom detection as they were going about their daily lives. So this task is actually very challenging because we have unknown daily activities which can create a confound with the symptoms. So for example, if I'm doing egg whisking to make breakfast in the morning, that can look very similar to a tremor, but it's not actually a tremor because I'm doing this motion on purpose. And then we also might have challenges with observability with respect to the label. So you can see in this case, this patient has a significant tremor on her right hand, but if she happened to be wearing that sensor on the left hand, we may not actually, there may be significant tremor, but we may not be able to detect it because of where the sensor is located. So how could we solve this problem using machine learning? So this is a classical supervised learning problem. We basically have our sensor data, and what we would like to come out with is a symptom label. So in the simplest case, we could consider just like a 2-class classifier, or is this bradykinesia or is it dyskinesia? So if we, with kind of like the standard machine learning approach, is what we would do is collect a large data set, collect excellent labels, and train a neural network. So we know that this can be done because we've actually solved similar problem like this this is, I'm highlighting here work for my lab, but lots of other people have done this this as well. So if we have a large amount of data, we can easily solve this problem. So I'm illustrating here another project that we did in collaboration between the University of Waterloo and Push. And Push is a company that develops a single wearable IMU that is worn for gym exercise monitoring. You can see the picture there of this IMU that's worn just below the elbow during the performance of gym exercises. So this work was led by my former PhD student, Terry So in this project, we were able to show that we could very accurately distinguish between 50 different gym exercises using a very simple deep learning classifier. So the idea is that we take a short window of time series data from the IMU sensor that's worn on just above the wrist. And we input this data into a neural network, and then the network outputs a class label, in this case, the exercise being performed. However, the secret sauce in this project is that we had access to a very large data set that was collected by PUSH, our industrial collaborator. So what they did is they distributed this project to a large population of university athletes. And these athletes all engaged in kind of set workouts that were specified by their coach or by their trainer. And so we had like a very motivated group of users that were generating very nice labels. And we had access to over 450,000 repetitions from over 1,500 athletes. And when you have access to this large data set, you can see here, at test time, we were able to achieve close to 90% accuracy with 50 labels, even from a single IMU. So that's great, but unfortunately, in our PD data set, it would be very, very expensive to collect such a large labeled data set from PD patients, because we would need both access to the participants, but also accurate labels about the symptoms, which are currently only able to be generated by clinicians. So what we had access to instead was a much smaller data set that was collected by our colleagues at the Schön Clinic. So this data set consisted of 25 patients who wore an EMG band in daily living conditions. So they were at home and they were performing their usual activities, but during the day, they were accompanied by a clinical expert who labeled each 1-minute segment with a symptom, the symptom severity, and the activity. So you can imagine the cost of this data set and the cost of this labeling. So we only had 25 one-day sessions. So what we observed when we looked at this data, just like visual analysis, is that we observed some variability across patients. So patients were engaged in different daily activities. They had different symptoms and different symptom severities. And they also had different sensor placement and body poses. So you can see, sometimes, for example, even just sitting, sometimes they were sitting, with the hands like this, and other times they were sitting with their hands like this. So how can we improve our model performance when we have a small data set? So one popular idea in machine learning that originated from computer vision applications is the idea of data augmentation. So the key idea here is that certain variations in the data should not change the label. And if I know what those variations are, I can generate additional data by augmentation. So in this example, let's say I'm training an animal classification model, and I have a single picture of a quokka, which is quite a rare animal, and maybe pictures are difficult to obtain. So I can generate additional samples by using my single real image and applying variations such as blurring, such as rotating, modifying the background, and so on. And basically what I'm saying to the classifier is, whether you see this kind of image or, this image rotated or blurred, that is still a quokka. And so so this kind of helps to make the classifier more robust, and it helps me to generate additional data without the expense of having to actually collect additional pictures of the quokka in the wild. And so we wanted to apply this idea that we borrowed from machine learning in vision to time series IMU data. To deal with the variability in sensor placement in daily activities, as well as the small size of the data set, we proposed a variety of data augmentation strategies suitable for wearable sensor data. So in this table, what I'm showing is basically each column is a particular data augmentation strategy, with the leftmost being no augmentation. And we compared two classifiers, support vector machine and convolutional neural network. And what you see in the very bottom row is kind of what does the data look like after that particular augmentation strategy has been applied. And then in the two middle rows, you see the train and the test performance. And so the test is when we test this classifier on patient data, so that hasn't been seen before. So what we want to do here is generalize across patients, not just across different times for the same patients. And so you can see here different techniques for data augmentation. So things like jitter, scaling, cropping, rotation, permutation, magnitude warping, time warping, and some combinations. And for this application, what we found is that the most effective data augmentation strategy is to apply rotation. So what that means is applying random rotation matrices to the training set. And the other one that was effective was temporal permutation, where we basically shift the window start by some random amount. And with these approaches, we can increase the motor state estimation accuracy up to 87%. So what's the physical interpretation here is that basically what we're doing is we're varying the sensor pose. So where, how the sensor is oriented on the wrist, and that should not, so whether the person is holding their hand like this or like this as they're tremoring, it shouldn't change the label. And then also becoming robust to variety in the timing of symptoms within a window. Remember, these were all labeled in 1 minute, but maybe the tremor was only present in it didn't start right at the start of the window. And this temporal permutation basically allows us to be robust to that variability. So in the previous example, we took advantage of the insight that variations in pose are label invariant. So more recently, we have also been investigating whether we can also incorporate variability in body size and shape. So this work was led by my PhD student, Yan Ranjian. Basic idea is similar to the previous work. We have a small data set of human motions, and we want to augment that data set by generating additional time series based on that data. But now what we want to do is we want to create a model of the motion from the data, and then use OpenSim, which is a well-known human musculoskeletal modeling software package, to generate additional motion, considering variations in body shape and size. And so we use OpenSim to generate what this, we have an example motion from a real person, and then we use OpenSim to generate what those motions would look like if we had a person who was of different height, different body segment lengths, and so on. And then what we can do is we can use OpenSim to then generate, okay, if that simulated human is performing that motion, what does the corresponding IMU signal look like? And so we've been testing this idea in the context of fatigue estimation. So the task is to estimate the level of fatigue from a given motion. So we have a small data set of 10 participants who are performing various exercises to exhaustion. And we then use this data augmentation strategy to generate additional simulated data of different size users performing the same exercise. And we assume that this variation will be label invariant. So let me share with you a quick summary of the results. So we test the proposed approach by assessing the fatigue on data from unseen participants. So again, here we want to see if this can, by introducing this variability in body size, can we handle unseen participants? So here we're showing the classification accuracy for estimating fatigue on a 10-point scale using 3 different classifiers: convolutional neural network, recurrent neural network, and deep convolutional LSTM. And in the leftmost column, we have the results with no augmentation. And the 2 panels are showing the test accuracy and the correlation. So we then investigate the performance of different augmentation strategies. And we start with the ones that we saw in the previous paper. So we have rotation, jittering, scaling, amplitude warping, and time warping. So these are kind of the same ideas that we had in the previous study. So we can see here rotation and some of the scaling and warping techniques can be somewhat useful. But the rightmost column shows the performance when we use the simulation-based augmentation. We can see that making use of the parametrized user model to perform augmentation can significantly improve performance. So to summarize, we may be able to achieve continuous, accurate monitoring of symptoms from very convenient, easy-to-use wearable sensors. That could be a single wrist-worn sensors that, it might even be, the watch that you already have. And by using data augmentation that leverages some knowledge of the source of variability. So for example, if we know that some of the variability is due to differences in body size or differences in sensor placement, we can really improve performance and reduce the need for costly data collection. Let me now switch to my second example. So in this second example application, I want to showcase a different learning context. So in this example, I want to focus on the case when we simultaneously want to learn a mapping and the policy. And as well, I want to highlight here that we have the case where the user model may be very individual and may be changing with time. And so we may not be able to take advantage of data from other users. We have to actually individualize and learn from a particular user. So we're staying with Parkinson's disease, but now I want to focus on gait therapy. So as we already saw, Parkinson's disease results in a variety of motor symptoms, and some of them impact gait. So a common symptom is called freezing of gait, and you can see an example of what freezing of gait looks like in the video on the left. So you can see the person just feels like they can't move anymore, and then even if they are able to move, they make very small and halting steps. So it turns out that this freezing of gait symptom can be alleviated by providing cues on where or when to step. So that's what you can see in the video on the right. You can see that on the floor, there are some basically white tape that gives the user a cue of where to step. And this cue can be very helpful to help the user basically overcome this freezing of gait motor symptom. So it turns out that this approach can be implemented with visual cues, which we saw in the previous video, but we could also use a variety of cues. So it could be visual cues, it could be auditory cues where you basically play a sound, or it could be haptic cues where you tap the person. Now, most existing approaches will generate fixed cues with no adaptation to the user. But there's been a lot of recent work looking at human-in-the-loop optimization for gait rehab for other conditions. And we were interested to see whether doing actual individual optimization to the user would result in better performance. In this case, this work was led by PhD student Tina Wu. So in this case, to generate an effective cue, we need to think about all the factors that might influence the person's ability, first of all, to perceive the cue and then to respond to a cue. So this might be influenced by their underlying health condition and mobility, because they maybe have, even if we want them to make bigger steps, maybe because of other comorbidities in addition to PD, they may not be able to do so. Their ability to perceive the cue, so for example, if we're using auditory cues and they're hard of hearing, they may not be able to perceive the cue, as well as their relevant PD conditions. So their severity of symptoms, the effectiveness and the timing of medication, and so on. And their responsiveness to the cue might also be impacted by their affective state. So how motivated they are to participate in the rehab, their current mood, their outlook. And so you can see that this, the responsiveness to cue is influenced by many factors that are likely to be very individual, and also that they may be changing at different time scales, right? So we have this kind of like long time scale of disease progression, but we have also these shorter time scales of like the medication half-life, as well as, the person's mood or motivation to do the rehab. So what we would like to do is we would like to develop an individualized approach to learning what's the best cue to give to this participant. So here is kind of a diagram of the proposed approach. So we have our human walker who is undertaking gait rehab, and we measure their gait with an IMU that's located just above the knee. And then we provide them with a cue to correct their gait. And in this case, we'll use an auditory cue such as a beat. So now from the IMU measurement, we want to estimate the gait parameters such as the step size and the cadence. And then once we've estimated those parameters, we now want to learn the individualized model on how the cue influences the human gait. And so we learn that from the data that we obtained during the interaction, right? So we're providing some cues, we see how the person responds, and we learn this model online. And we use Gaussian processes to do this. Now, once we have this model, now we can use model-based optimization to select the next cue. And so we then use that to generate the cue. And so we want to run this entire loop online so that we can be continuously learning the model and adapting to each individual user, as well as to any changes in the user responsiveness over time. So let's look at those three components in a little bit more detail. So the first one is the gait model. So here we model the gait as periodic, as a weighted sum of sinusoids, and then we learn the model parameters with incremental updates from IMU signal data. And you can see that in the panel on the right. So you can see within just a few steps, usually 8 to 10, we can lock in to the estimate of the model of the gait and estimate the gait parameters accurately. Then we want to learn the model of cue influence on gait, and we use Gaussian process to do this. And then we use optimization to generate the next cue using our GP model. So let's see what that looks like. So we start from not knowing anything about the user. And so we have this initial exploratory phase where we generate some cues, and then we see how the person responds, and we use that data to build up our model. And then once we have enough data to be able to predict the responsiveness accurately, then we have the converged phase where now we are generating cues that are appropriate for the person. And what you can see here is one of the things that we really care about is we want the learning to be fast so that the person is not spending a lot of time just like responding to these, random and not useful cues. So this convergence happens in this example I'm showing here is around 70 seconds of data. So we wanted to test to see whether this, kind of individualized, personalized approach would do better than the current state of the art. So we ran a study first with 25 healthy participants. So we had 7 experimental conditions where first we start them practicing. So we, have them wear the IMU, we show them the cues, make sure they understand what's going on. Then we record a baseline. We just ask them to walk for 6 minutes without any cues so that we can figure out what's their preferred gait speed. Then what we're going to try to do is we're going to try to change their gait speed with cues. And we're going to try to change it in 2 directions, either up or down. And then for each condition, we're going to try to change with 3 different strategies. Either fixed cues, so just provide a constant beat at the target rate. Proportional cues, where we basically cue the frequency cued is proportional to the error. And then the adaptive cue, which is our proposed approach. And so then we randomized these conditions. And then at the end, there's a short debrief and a subjective survey. And what they're doing during their when they're walking, regardless of the condition, they're basically just walking in a big circle. Okay, so let me share with you the results. So here I'm showing the on the left side the mean absolute error between the target cadence and the actual cadence. So lower is better. And I'm showing separately the up targets and the down targets. And then here I'm showing the 3 different conditions. So A was the fixed, C was the proportional, and then E was the proposed. And here in E, I have 2 phases, the exploratory phase and the convergence phase. And so what we can see here is that for both the up and down conditions, the adaptive strategy achieves the lowest error after convergence. Of course, we have a high error during convergence because this is while we're still trying to learn and we're not really using the optimization appropriately yet. The other thing that was really interesting to see is that the adaptive strategy minimizes the % of the time the cueing is on, which is shown on the right-hand side of the panel. So to summarize, the adaptive approach has the highest error during exploration, but the lowest after convergence. One thing that we found when we looked at how cues were being generated is that the cues did differ depending on the participant's response and their ability to keep to the beat. So actually individualization was useful. We also saw from the survey responses that there was a higher cognitive load with the adaptive strategy. And we weren't sure if this was kind of like a good thing, but actually when talking with our clinician collaborators, they thought that actually this could be a good thing because it could help bring attention to the task. And we're currently testing this with patients. So I don't have any statistical results yet, but it's been very interesting to see that actually we are able to, not to the same extent as a healthy participant, but with some patients, we are actually able to use this strategy to help them achieve the target speed more effectively. So I'll just end with some thoughts on some of the things that we're currently thinking about and thinking for future work. So one thing that I'm really interested in, I've showed you here a couple of examples where we're using learning and we're also kind of taking advantage of some knowledge, about the patient or about the patient's body or the sources of variability. I think we could do this in the future a lot more effectively. So thinking about how to take advantage of learning while also incorporating things that we know about. Do we know things about the patient? Do we know things about the disease that we can incorporate to help our model be more effective? And then this question of when is it better to learn an individualized model, and when is it better to learn a model for the entire population? Of course, I think this will also depend on the context and the amount of data available. So I'll end there. Thank you very much for listening, and I'm happy to answer any questions.
Thank you, Dana. Are there any questions from the audience? Maybe while people are thinking, I can start with a question. So yeah, I think it's quite interesting that by adding the simulator generated data, the model can get a big boost. And I mean, for a lot of deep learning or reinforcement learning approach, like the data is really the key limit to like how good the data could perform. And I think it kind of feeds both ways, that if you have a really good simulator, you can generate great data to augment the model. And then, with the model, then you're able to develop a better simulator. But when you don't have any knowledge, then it's also difficult to develop a realistic simulator. And then that's why I see all of this, I guess, seem to real gap in a lot of the robotics research. So what do you think would be an effective approach for us to develop better simulator, better modeling of human behaviors?
Yeah, thanks, Lemon. I think that's a really good question. So what I hope that actually my examples here are showing is that, of course, coming up with a model of a person that fully captures all of the, influences on their behavior and influences on their motion is very, very difficult. And, if even, I kind of gave some examples of the things that could influence the person's motion. It could be the severity of the disease, but it could also be their, they might have some other comorbid disease. They might also, have recently had, joint replacement surgery. And so that will also influence their mobility. It could also be their motivation, their mood, and so on. And so developing a model that captures all of that is, very, very challenging. But what I hope I'm showing with some of this work is that actually even having very simple models that only capture a part of the variability, so in the two examples that I showed here, in one, we just captured the variability of like people can have, when they're tremor, they can have their hand in different poses, right? So that's only capturing a very small, part of the full variability, but even that can be very useful. And then similarly, with our simulator in OpenSim, we didn't capture the full variability. We didn't try to model inside OpenSim the changes in motion as a result of disease or as a result of other comorbidities. But still, even just kind of like this, kind of simpler models were able to help improve performance. And I don't doubt that if we had better models, we could improve performance further. But I think, it points to this kind of like, actually there's utility in this incremental approach, is that, we can basically start with simple models that can help our, our systems. And then, the other thing that I showed here is that the way that we're doing this is we're not doing this by pure simulation. We're doing this by data augmentation, right? So our simulation is based on some underlying, small amount of data that we have actually collected from real users.
Yep. Thanks, Dana. Okay, so ask another question then. Yeah, so with I guess the examples that you give, most of the data are measured with the IMU, so mostly it's from the motion of the person. So do you think by including multimodal data, for example, we could have physiological signals from like the EMG or other types of sensors, would that improve the model's performance?
Yeah, absolutely. So I think, I'm showing here IMU data, but of course, if we had additional data, it could improve performance. But I think the caveat there is this trade-off between better data quality and, kind of usability in kind of broader settings. So if we're talking about motion, like, of course, I would have loved to have all of this data in mocap, with very accurate, like 12 camera systems, it being collected at 100 hertz or 200 hertz. But of course, then like the deployability of that kind of system to anywhere beyond the lab is very minuscule. And so I think that that's always the trade-off of this, like the quality of the data versus how easy it is to collect. And because I think ideally we want to be moving towards systems that we can deploy in people's homes and clinical settings as well.
Yeah, definitely. Okay. Any other questions from the audience? Team, I see you have switched on your camera. Do you have a question?
It's okay. Thank you. Thank you for the presentation.
Okay.
Maybe just a small question. When you try to multiply the data and to extend the data by different artificial methods, if there is a possibility that we get artifacts in this data on further recognition, I mean, when you distort the picture, you somehow implement some faults that a camera could infer. That's why you're using different filters like blur and so on. And in this way, that's always a possibility that we get artifacts after.
Yeah, so this is a great question. This is kind of like the key assumption of doing any data augmentation, right? Is that the augmentation is label preserving. But if you change the data in such a way that the label that is associated with the original data piece is no longer accurate, so if you think about the picture of the quokka, if I now crop the part of the image where actually the quokka is, now the label is that label is no longer correct. And we definitely face the same issue when we're doing data augmentation with wearable data. And I would argue even the problem is harder because, like, I think with image data, it's very clear to see, like, okay, now I've cropped the quokka out of my image. My data augmentation has failed the assumption. But sometimes with time series data, especially if you have so with IMU data, you have six channels. So, gyro and accelerometer XYZ, and possibly, 9 if you have a magnetometer as well. So looking at that time series and saying, oh, now the label has changed might be much harder than with visual data. So you're absolutely right that if you're doing data augmentation that changes the label, then, you will not see a benefit in performance. And actually, kind of figuring out when that's happened is a very challenging problem.